Okay, and finally, the last two pages here, I'm introducing this idea of simplified radical forms. So we know, like, if we see like a perfect square, like for example, the square root of 9, I mean, we know that's the number 3. But something like 12, 12 is not a perfect square. And we can grab our calculators and come up with a decimal approximation, but we need to get good at writing these down in exact form and simplified radical form. So the thing that I'd like for you to do is off to the side of this paper, and I realize I don't have this here, but way off on the side of this first page that says Honors Math 1 Simplify, I want you to write a list of perfect squares. So for example, we've got 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7, not to the 7, 7 squared, 8 squared, 9 squared, 10 squared. So these are pretty straightforward, right? It's like 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. So here's a list of the first, the perfect squares from 1 through 100. And what we're looking for, or we're looking for perfect square factors inside of this radical. So when I look at the number 12, right, I recognize that I can divide that by a perfect square. I can divide that exactly by the number 4. So I can rewrite this as the square root of 12 is the same thing as the square root of 4 times the square root of 3. Now, because these are factors inside, right? It's a multiplication. I can break this up into two separate radicals. I couldn't do this if these were terms, right? If this was root 4 plus 3, but I can do this because they're radicals. So I can rewrite this as the square root of 4 times the square root of 3. And what's nice about that is the square root of 4 is just the number 2. So I can write this as 2 times the square root of 3. So square root of 12 is the same thing as 2 root 3. Now, when you get answers, it's going to be a little like I think I did that right, but you're going to be a little uncertain for a while. So I really encourage you to take your calculator and look at the square root of 12 as a decimal, and then compare that with 2 times the square root of 3. And you can see in both cases the decimal values match exactly, right? Root 12 and 2 root 3 are identical to each other. 2 root 3 is the simplified radical form of root 12. And if you look at the final answer here, right, the radical inside this root 3 contains no perfect square. In fact, root 3 is prime. So the 3 inside of the radical is prime. So we're done with that. Now, occasionally, if I look at the square root of, whoops, not that. If I look at the square root of 196, yeah, occasionally when we're asked to write simplified radical forms, it's as easy as recognizing, oh, that's a perfect square, right? So this is just the number 14. In fact, it's probably worth it to look at that and just see, hey, is that a perfect square? So this is the number 14. Um, that's pretty straightforward. Let's look at number 4. So I'm looking at 147, and I'll try this trick again. I'll say, hey, what about the square root of 147? Is that a perfect square? And it's not. So I'm going to start looking at my list of perfect squares, and those are just off the screen over here on the side. And I'm going to go through and try and divide that by some of those. So if I took 147, I'll try and divide it by 9. Not happening. 147 definitely is not divisible by 4. Um, 147 divided by 16, it's not happening. 147, it's definitely not divisible by 25. So you might ask yourself, well, then why are you trying it? I don't know. I'm desperate. 147 divided by 36. I got nothing. 147 divided by 49. That's what? There we go. Wow. I thought all hope was lost, but it turns out it's divisible by the number 49. 49 is a perfect square, so this I can rewrite as, I said it was divisible by 49. So I can rewrite this as the square root of 49 times 3. 49 times 3 is root 147. Now, I can break this up into two radicals because these are factors. They're not terms. So I can rewrite this as root 49 times the square root of 3. And root 49 is just the number 7. So what I have here is 7 times the square root of 3. And again, I'm going to check this. If I look at the square root, I think I got it up here earlier, right? I'll just go up. I did the square root of 149 to start with, didn't I? Yeah, the square root of 149 was 12.12, etc. So I'm just going to compare that with 7 times the square root of 3, and that gives me exactly the same thing. So this is the simplified radical form of 147. And then finally on the back, none of these variables had squares in them. So if you see, expressions with variables inside of them, like radicals with variables, if you're taking a square root, and if I had, for example, x squared inside of there as two factors, I could have brought that out front, but none of these have squared variables. So all I'm looking for, again, is numerical. I'm looking for squares in my numerical coefficients. So I do see that it's got a negative out in front of the radical, so it's going to be negative. And 18 I know is 9 times 2, so I could handle that much. So this is 9 times 2xy. Well, the x is not squared, the y isn't squared, it's not x to the fourth or x to some even power. So I'm going to have to leave my variables inside. So I can break this up as the square root of 9 times the square root of 2xy. And I know that the square root of 9 is 3, so I can write this as 3 times the square root of 2xy. Now, the variable part, they weren't perfect squares. They're going to have to stay there. I can't really check that with the variables, but I can compare root 18. Oh, I forgot it was negative. That's important. So I can compare root 18, negative root 18, or the opposite of the square root of 18, with the opposite of 3 root 2. So I want to just compare that and see if they're the same. So I'm going to enter the opposite of the square root of 18. And you can see I get negative 4.24. And I'm going to compare that with the opposite of 3 times the square root of 2. And I get exactly the same thing. So this is simplified radical form. There's no perfect squares left behind inside of the radical. All the perfect squares came out. So I realize this is probably a bit much. So do as much as you can. I would say focus on the first page and try to get at least half of the second page finished.